All right. Moving along. The diving board. Well, we've already done the diving board problem, but we can go ahead and do it again. So we've got a diving board. We've got two pillars. This time we've got a diver about to jump off. All right. So, forces exerted by the pillars. Diving board has negligible mass this time. So we just have the mass of the person times g. We've got the support force from this pillar. Now we know that this is going to be downward. But in general, if you're not sure, it's a good idea to call it upward, and then you can see what it works out to be. And just for kicks, this time I'll set my pivot point to be right there at the other pillar, so you can see how that works. So let's write our torque equation. What do we have? Well, we've got mg. How far away is that? Well, one is 2.2 meters from the end. The other end is 9.7 meters away, so the distance between those two is 9.7 minus 2.2. No, I'll just leave it as r for the moment. R diver, massive diver. And then from this guy, and that's counterclockwise, or clockwise, it would cause the board to rotate this way, so that's negative. Minus, this guy is also pushing up here, would cause the board to rotate clockwise. And 1, and how far, that's, again, some distance away. And both of these are acting perpendicular to the diving board, set that equals 0. And we can plug in numbers. Mass of the diver is 68, g is 9.8, and how far away is he from the pivot point? Well, this is from here to here is 2.2, from here to here is 9.7, so we subtract those and get 7.5, and we already said this is 2.2 meters away. So then we can solve for that force. You'll notice from the sign that we're going to wind up getting a negative number, which makes sense since we learned that it's downward. So it's about, we'll call it 2270 newtons in the downward direction. Okay, and then from our force equation, we can then calculate what the value of the other force is. We just have these two forces and then third force, gravitational force downward. So the normal 1 we learned is minus 2271, etc. Normal 2 minus 68 times 9.8. So we learned that the force from that second pillar is, that becomes positive when we move it over. This becomes positive, and we get about 2940 newtons upward. All right. The diving board had a mass. We just incorporate that into our torque equation. Equation would be exactly the same for the diver and the board, but then we would have an additional force, the gravitational force acting on the diving board. The mass of the board times g, which would act in the middle of the diving board. So that would be a distance 9.7 over 2 from the end, which is 4.85. That's going to be 4.85 meters. So its distance from this pivot point would be 4.85 minus 2.2. So then we have minus mass of the diving board times 9.8 times 4.85 minus 2.2, which is 2.65. And then we could solve for the value of that. And then our force equation would just become N1 plus N2 minus the gravitational force on the person minus the gravitational force on the board equals 0, and we could solve and plug in there. Right, shelf of mass 1.3 kilograms and width 1.01 meters is attached to a wall at one end and additionally supported by two chains each anchored to the shelf, making an angle of 48 degrees above the horizontal. Two objects are resting on the shelf. One has this mass and is that far away. The other has this mass and is that far away. Find the force provided by each chain, the force exerted on the shelf by the wall. I probably should have left a little bit more space there, just if for nothing else to draw a good picture. So I'm going to take the time to draw a good picture here. This is my chain, angle 48 degrees. Two chains, side view, you only see one. All right. The length of this, or the width of the shelf is 1.01 meters. And we have two objects. One is 0.11 meters from the wall. And it has a mass of 2.04 kilograms. Another is 0.56 meters from the wall. And has mass 2.04 kilograms. And I should have stated the shelf has negligible mass, so we'll say the shelf's mass is negligible. Or actually, we'll say that the shelf has a uniformly distributed mass of 1.2 kilograms. Yeah. So then what forces do we have acting? Well, we've got the force from the chain, from the two chains. So since there are two chains, I'll call it 2 times force of chain. And then you've got a force exerted on the shelf by the wall. Well, in the horizontal direction, it's going to go this way. We've got some unknown force from the wall that'll have an x component and a y component. We've got a gravitational force on this guy. Oh, I wrote the same mass for both of them. Sorry. This one had mass 4.21 kilograms. And we've got a gravitational force on this guy. And halfway down, which would be at 0.505, we have the gravitational force, mass of the shelf, times g. I'll call this M1, M2. Okay. Where's a good place to set the pivot point? I'll choose this end. So there's my picture. All right. Now, looking at our picture, we want to write that torque equals 0. So what do we got? Well, let's just go down the line. We've got the gravitational force on this object, m1g. That's a distance. Well, actually, I'll just put in numbers right away. The gravitational force in this object would cause this guy to rotate clockwise, so we'll call that negative. The mass is 4.21, so the force is 4.21 times g. Distance from the axis of rotation, 0.11 meters. And that's perpendicular to the shelf, so sine of 90, which is 1. Okay, then we've got minus mass of the shelf times g. I said the mass of the shelf is 1.2 times 9.8. And if the shelf is uniformly distributed, that's going to act halfway down. Half of 1.01 is 0.505 minus mass of this guy, 2.04 times g, and that's acting 0.56 meters from the axis of rotation. Apologies for splitting onto two lines. And this chain would tend to cause the board to rotate the other direction, so that's a plus 2 times force from the chain, and that acted the full length of the shelf away, so that's times 1.01. And all those add up to 0. So from that equation, we can get a value for the force of the chain. We move these all over to the other side of the equation, they're going to become positive. So 4.21 times 9.8 times 0.11 plus 1.2 times 9.8 times 0.505 plus 2.04 times 9.8 times 0.56. That's going to be equal to 2 times force of chain times 1.01, so divided by 2.02 gets us the force from the chain is about 10.73 newtons, which I'll store as F for the moment, force from each chain. Okay, then we can write forces in the x direction, which is the easier one. What forces do we have in the x direction? Well, not a whole lot. We've got the x component of the force from the wall pushing to the right, and we've got the x component of the forces from the chains pushing to the left. So plugging in that stored value, times 2 times cosine 48, gives us that the x component of the force from the wall is 14.358 something. I'll store that as x. In the y direction, we've got a lot more terms. We've got a y component of the force from the wall. We've got an upward 2 force from the chains sine 48, and we've got downward mg for all this stuff. For just the force, we can just treat them all together as though the shelf and the two objects on it are all one object. Set that all equal to 0. Again, using that stored value. When you move this over, that'll become positive 2.1 plus 2.04 plus 1.2 times 9.8. And then when you move this over, it'll become negative minus 2f sine 48. And that's equal to the y component of the force from the wall, 57.06 something. I will store that as y. And then as always, we do our usual square root of x squared plus y squared for magnitude. So the force from the wall is about 58.8 newtons at 75.9 degrees above the horizontal.